In the context of lower oil prices, maintaining low production costs and high productivity is absolutely key for the survival of the whole value chain. One of the most important factors in this low production cost is the uptime of the production assets, and most particularly of the critical equipment such as the pumps. What we do is we bring a health scorecard of the pump. We match it to typical faults like bearings, stator, rotor, alignment problems, and we are able to give early signs of failures that will give time to the operator to organize itself, to anticipate a failure and take the necessary steps before it's going to start incurring a lot of losses. So how does that work? We have an innovative technology approach here. We use the analysis of the electrical signal. What we do is we will put some small sensors, clamp-on sensors on the lead power cables of the pump, connected to an analyzer that will record and analyze the signatures of the equipment. What I mean is, if I take the example of a rotating machine, let's imagine that it has a hard point at a place. That will impact the torque and the current, and our device with its algorithms is able to detect exactly the location of the hard point by matching it to the predefined signatures. Now, how do we differ from existing solutions? Most existing solutions are based on vibratory analysis, which has two limitations. A, it creates a lot of false positive in noisy environments. Imagine an oil rig, there's a lot of generic vibration everywhere, and that will confuse vibration monitoring systems. Our system is totally immune to the general vibratory noise because it just looks inside the machine. And B, some assets are just not accessible to vibratory sensors. An immersed pump at the bottom of the ocean, you cannot install a vibration sensor, whereas you will always access the power cables because by definition they are available. Now, how do we prove that that works actually? So we spent 3 years working on a bench. So here we have a lot of motors with different test sets. And for example, we will take a bearing, create a default on it, some difficulties or lubrication problem, and run tests so that our algorithm will learn how to match the signature of a given default to the signal. We also work on other types of defaults. For example, we work on stator. We simulate problems on the stator, on the rotor bars. And mostly, we also work with real machines in real operating conditions. That has been deployed on wind turbines, traction motors of trains, large 20 megawatts compressors with air liquide, and also vent fans for aircrafts. Now, in terms of go-to-market and commercialization, we will work in 2 phases. First phase is to the proof of concept of the technology. So we can equip like 4 or 8 machines for 1 or 2 months just to prove that we are able to understand the machine itself. And we can also work on bench if the operator has machines that have a default. We put them on a bench, run our system, and prove that we locate correctly the faults. And after that, we of course go on a scale deployment.